Okay, now we want to start to answer the question, how then we get a pure alcohol from aldehyde and ketone? We know that the hydride, we cannot use the hydride from NaH, because when NaH deassociate, it give you Na plus and also hydride ion. So this hydride ion, we know that it will never be able to be used by the by the aldehyde or ketone, because it will almost always react as a base, meaning that this hydride will still we sort of like will attack the smaller molecule like the alcohol or like the halides, and giving off this hydrogen gas. Okay, so, and then we say that okay, then we can use the what we call the reducing agent. But what make this reducing agent different than NaH? So if you look the reducing agent that we will use, NaBH4, look at the structure. You have this structure. So this structure, if you look, there are negative charge, and we know here in this case the negative charge here doesn't mean the two electron. So meaning that this thing, if it will behave like the nucleophile, it will start the bond breaking from the bond BH bond, not from the what we call from the this apa ni negative charge. So when this borohydride, in order for borohydride to behave like the nucleophile, it need to find the electrophile. So that's the reason before it reach so it's not free. In this case, it's not free like the sodium hydride like that. Sodium hydride, you put in the water, it will dissociate. But this borohydride and ion, in order for this what we call these two electron in this bond, be boron and hydrogen, to be broken and attack to another electrophile, is to find another electrophile. So in this case, we know that this thing, the what we call this aldehyde here, is electrophile. So now this thing, this what we call this nucleophile, we found the opportunity to attack this thing. So this hydride here will not be lost to this something like this. Okay, so that's why the hydride here can go and attack and attach to this what we call the carbon compound. So what will happen then? So when you attach the hydride, when the hydride attach to this thing, for sure that you make a bond, and some bond must be broken in order to fulfill the Oxted rule. So this we have learned before. It will create this oxy anion, and also this what we call this intermediate lah. We can say the BH3 lah, the leftover from this lah, from what we call from this reducing agent. Okay, we know this thing. Okay, let's look this thing. What is BH3? BH3 we learned before. BH3. So for BH3, you can see this boron, they adopt sp2 hybridization, meaning that is planar. So sp2 mean what? sp2 mean that you have s orbital field, and then you have 2p orbital also field. Because why I say it's field? Because the s and 2p orbital here is used to make the bonding. But we know also that they are the p orbital, they are another p orbital, because p we know we have px, py, and pz. So there are one p orbital that is left unhybridized. Okay, so meaning that if you look the borohydride, this boron with the BH3, so BH3, so what does it mean? This special molecule, they have this what we call MTP. Let me remove this color. Let me remove this thing. It have what we call the MT. Let me take the. They have this MTP orbital, which is ready to accept the 2 electron. So that's why here this is the reason. The oxygen and ion produced in the first step can help stabilize what? The electron deficient BH3 molecule by adding it to the MTP orbital. So this MTP orbital. That's why now you have this oxo anion. So this oxo anion, okay, oxo anion. And this thing, that the one BH3 is somehow electron deficient lah. So now because this is electron rich, this oxo anion is electron rich, it will act as a nucleophile and attack this empty orbital. So that's why you can see here the oxo anion attack the boron BH4 again, BH3 again. So you get something like this, and then this borohydride become the anion again, and it seems like above, and then it will repeat again and again and again. Okay, so we have the trivalent boron anion again, which could transfer its pair of electrons to another molecule of aldehyde. So this is this part, and then process can continue so that all 4 hydrogen atom in borohydride anion could be transferred to the molecule of aldehyde. Okay, so if let's say we just have this borohydride anion, and also we have this carbonyl, or whether it's aldehyde or ketone, what will happen? It will continue become like this. Okay, it will continue become like this. So in practice, this rarely efficient compared to when the reaction is carried out in water or alcohol solution, because because remember, the idea is that we want to get pure alcohol. Here the problem is that we don't supply the reaction with the what we call the proton. So if let's say we give water, or we give alcohol, meaning that we supply, or we make this reaction in water or in alcohol solution, then this thing will attack the proton. Okay, the proton coming from the water, because remember, water is what? H2O. So meaning that you have O, you have H. Okay, so the O minus there, the one that I draw again, so the H R. Okay, so this one will attack this thing, and then this will attack this thing. So this what we call oxo anion will find the proton there. Okay, so this is what happened here. Oh, see, this is too much, so let me remove. It is all ink. So you can see this what happened here and here. So this we use the water. So you can see you have this what we call, this is what you have: carbon, you have H, and you have R. You have this, you have R lah, because this is aldehyde. So you have aldehyde, and then you use a reducing agent here. We know when you use reducing agent, you add a bond. You add this what we call, you add one bond here. So let me put in the color here. You add one bond there, but then this thing, the one that is left before, because it can attack the H, because they can attack the hydrogen from the water. Let me I draw the water here, because it can sort of like attack the hydrogen from the water, and then this bond will go to here, creating the ozonium. Let me put carefully, creating the ozonium ion. So then that's you get the OH there. Okay, same like this. So this they use alcohol. So this is what? This is ketone, because this R and also this R. So this is ketone. Okay, you use the reducing agent, and then the same idea, reducing agent meaning what? Meaning you add another bond to this the double bond, so you get this extra bond. Okay, that's so far so good. But the protonation of the oxy anion, so this one, the one that I show here, is happen because you supply the alcohol here. Methyl alcohol, the same like water. So methyl is basically CH3. So MEOH is basically CH3, and then you have OH. So OH here they have a two lone pair. So basically this thing will sort of like the oxy anion here, this thing will sort of finding the H here. They will try to take the H there. Okay, now we want to see what else can attack the Carbonyl group. So we want to see the attack by organometallic and also Grignard reagent. It's not Grignard, it's basically Grignard reagent. Okay, so we first start with the organometallic. The term itself, organo means that this carbon, there are hydrogen. Metallic is metal, for example lithium, magnesium. So when you have carbon and then you combine with the lithium, then you get the organometallic carbon lah, CH whatever lah, CH3 yeah, like that. So this is organometallic. You combine organic material with the metal. Okay, so carbon metal bond, metal, lithium magnesium is highly electropositive. So if you look here, if you look this what we call the lithium or magnesium is highly electropositive, causing carbon to be partially negative. Normally, okay, this I put this first, but normally when you see the what we call, when you see this thing, the carbon double bond O, so you know that the electron will be sort of like tend to be at the O, so carbon will feel the partial positive and this partial negative. But when now you have the what we call the lithium or the metal lithium or carbon magnesium, the opposite will happen, because this magnesium and lithium is electropositive, so carbon is more electronegative compared to magnesium and lithium. So what will happen then, this thing, the electron somehow withdrawn to the carbon. So now instead of this part, instead of carbon become partially positive, in this case carbon become partially negative, whereas this metal become partially negative. So that's why, hence, lithium and chloride or magnesium carbon is powerful nucleophile. Because why? Because carbon here now have more electron density. So you have more electron density, you are more ready to give the electron off, and that can attack the carbonyl group to give alcohol and forming CC bond. So we will see later lah. Okay, let's look at the reaction. Let me remove this first. Let me remove this. Let me erase this first. Okay, let's see the reaction here in the box. Okay, so you can see this is the aldehyde, and then you have this organometallic. Because of this metal, so remember this is CH3, metal lithium. So metal is organometallic. This they give this partial negative to the metal, so the metal will be ready to donate their electron. So this lithium, the organometallic, become the what we call, become the nucleophile. They become nucleophile. Okay, and this become the electrophile. So they will attack each other lah. So before we go further, let's see at this reaction itself. You can see this number 1 and number 2. In fact, we have seen this before when we talk about the ester reduction to the alcohol. We also see number 1 and number 2. So if you look here, number 1 and number 2 means the first, this one, the Meli here, or methyl lithium methyl, is added to the aldehyde in the THF solvent. We will talk about this THF solvent, what it does mean. So the THF solvent, that's why they have this. This is solvent. Then the reaction occurs. Then water is added in a separate step only when all the Meli has reacted. Okay, so that's the meaning of numbers here. Okay, it doesn't happen simultaneously, step by step. In fact, water should not be present during the addition of Meli or any organometallic reagent to carbonyl group, because water destroy this thing. Water destroy organometallic rapidly. If you look here, water, if you see before, water is like this. Okay, you have the what we call the lone pair there, and then if you have, for example, nucleophilic, let's say you have a nucleophilic there, this nucleophilic will attack the water, and then this bond will go there, and then you get ozone anion and whatsoever there. So in this case, organometallic, this thing will sort of attack the hydrogen here, and then the lithium, the metal here will make a bond with the hydrogen, and then lithium will make a bond with the OH, and then this organometallic will be no more, destroyed. Okay, so if you look in the beginning, this lithium metal can behave like nucleophile, but then when it become methane, it's like neutral. It cannot become nucleophile, or it cannot be the what we call the electrophile. Because why? Because the methyl and the hydrogen is not really what we call far in the electronegativity difference, so there are no partial difference in terms of electron distribution in this methane. So instead of become the nucleophile, when you react with the water, when the organometallic react with the water, it become this, it will turn into this dull methane. Okay, so that's why it doesn't mean organometallic are destroyed by water. So that's why you need to put water later. But the question is, why then you need to put water? Why you need water after all? So that's because when you attack the carbonyl here, this bond, the pi bond will broken and goes to the oxygen. The oxygen become the oxygen ion. So this is the reason the oxygen ion need the hydrogen in order to make the alcohol. So as we mentioned before, the nucleophile from this charge, the negatively charged oxygen will attack the hydrogen, and then the bond between hydrogen and OH will be broken, and then you get the OH. So that's basically the mechanism of attack of carbonyl by the organometallic. Organolithium and organometallic are strong base as well as strong nucleophile. So we have mentioned before why is that the case. It's because of the electropositivity of this lithium and magnesium, causing the carbon become more electron rich and can behave like a nucleophile. Okay, because they are so reactive. Organolithium usually used at low temperature in aprotic solvent. What is aprotic solvent? Aprotic solvent is a solvent that are no hydrogen bonding possible lah. For example, if you see water here, let's say I put this thing, let's see this thing. So this is water. Alamak, this is water. It's okay lah. This water, if you look the water, the nucleophile can make the, let me take another color lah. The nucleophile here can make a hydrogen bond with the ash here. So aprotic solvent is basically a solvent that make this hydrogen bonding not possible. So for example, this thing, I remove all this thing lah. So for example, aprotic solvent is diethyl and also tetrahydrofuran. Okay, so this example lah. Ether common, the ether, tetrahydrofuran and also diethyl. So that is common aprotic solvent. So aprotic solvent is just the opposite. So you have water, alcohol, because water and alcohol can make the hydrogen bond, so to the organolithium. Okay, so that's why when you want to use organometallic, whether it's organolithium, organomagnesium, you need to use this aprotic solvent lah, because in order to prevent the organometallic from being destroyed by the water or alcohol. Okay, water or sometimes dilute acid added later to the protonic. So you can see this thing, the water is added later. So this addition here, they are called work up. The process is called work up. Okay, so that's why the reaction is known as work up. Okay, addition to aldehyde gives secondary alcohol, while addition to ketone gives tertiary alcohol. So this thing and this thing, this is aldehyde, aldehyde, and this is ketone. So this is what we call organometallic, and this is the solvent, and this is the water. So it's the same idea, but I mean you will try to look at this and you will understand why it behave like this lah. Because this is simply because you have the hydrogen here, and then you have hydrogen here, and then you just sort of like replace, you add the phenyl. So the phenyl is basically this thing lah, the phenyl. So now the carbon here is attached to 1 and 2. I call carbon attached to another 2 carbon. So this is secondary, and because this alcohol is secondary alcohol. So in this tertiary alcohol, because this is R, and then when you do this organometallic reaction to this carbonyl, this N-butyl, which is also alkyl group, will be attached here. So carbon here will attach to 1, 2, and also 3 another carbon. So because this alcohol, this is tertiary alcohol. So the what we call the initial reagent, the initial starting material will determine also what will be your final product. Okay, sometimes you heard about the Grignard. What is Grignard? Grignard is basically more or less like organometallic, just the different, you have X here. X here is halide lah. So for example, methyl magnesium chloride. So chloride here is halide. So X here is basically halide, fluorine, chlorine, bromine, iodine. Okay, so you have methyl, you know this organo, magnesium is metallic, and this chloride, this X lah, this X. And another example, phenyl magnesium bromide. So you have what we call the let me put in this color. You have this organo, you have this metal, and then you have this halide. The mechanism for this thing is almost the same like the organometallic, because if you look here, it's the same thing. So just the difference, just you have this thing, you have the bromide or this halide or, attached to the magnesium, but the rest is the same. I mean, you need to add in the non-water condition first, and then you add water in the workup process, and that's it about the organometallic and Grignard reaction on the carbonyl group. Okay, now let's see what happens when the carbonyl group is attacked by water. So water, if you look the water molecule, you know that water molecule have the lone pair. That lone pair can cause water to behave like a nucleophile. So let's say you have hydrogen chlorides, and then this lone pair can attack this what we call the hydrogen, and this bond will be broken, and you will end up with the oxonium ion. So you have this, and then you have this plus, and then plus the Cl minus. Okay, so in this case we can say the water act as a nucleophile, but at the same time water can also behave like the electrophile. If we draw again the water here, and then we bring the some nucleophile, let's say I give nucleophile only, the generic symbol of the nucleophile. This nucleophile can attack the hydrogen here, and then this bond will go there, and then you will end up with the nucleophile with the water have a bond with the hydrogen plus with the OH minus. Okay, so in this case we can say that the water here act as a electrophile. So that's why people say that the water can behave like a base and also can behave like a acid. So because water can be nucleophile, can be electrophile depending on the situation. So when you add water to aldehyde and also ketone, you will yield what we call hydrates. Okay, so this is the mechanism for that. Let me remove all the ink. So if you look here, the water here have act as a nucleophile, attacking the hydrogen, making the pi bond on this what we call on this double bond goes to the oxygen. Oxygen will be become an ion, and the what we call what you get is basically another part that have bear the positive what we call positive charge, and because of this positive, then it become electrophile. So another water can behave like the nucleophile and attack again this part, and then the thing repeat again. What you end up is the OH there. But also remember, there are also the what we call the same thing also can occur here. Okay, but here you can see they are already, it's already oxy and ion, meaning that the O and bear the negative charge. So it's just this thing behave like a nucleophile attacking the water also, and here in this case the water behave like the electrophile. In this case water act as a nucleophile. Okay, so and then when this charge take steal the hydrogen, you get the hydrogen here. Okay, so this is basically what we call here, this is hydrate, they call it hydrate. Okay, so let me remove the ink first. So significant concentration of hydrate are generally formed only from aldehyde. Let me change the color first. If you look this, okay, if you look, this is what ketone, this is aldehyde. Okay, so this is basically formaldehyde lah, because we already know there are H, hydrogen, so this is basically formaldehyde. If you look here, look at this arrow, this and this arrow. So this meaning that it's favor the production, it's not favor the production of product lah. In this case, they favor the production of the product. So this is product, this is product, this is also product. Okay, so meaning that if you have aldehyde, it's much more, you can get more significant concentration of hydrate from aldehyde compare when you use the ketone like this. Okay, the reason being is that if you look at here, this hydrogen and hydrogen is small compared to this alkyl group, the R group is big. So now you have what we call here we put the idea of steric hindrance lah. We call it steric hindrance. Okay, steric hindrance is basically the hindrance caused by the bulkiness of the substituent. For example, this R is bigger than the H, so meaning that the nucleophile can attack easily for the aldehyde. It can attack easily because it's small substituent. The hydrogen only is very small, so that's why formaldehyde is readily react with water because its substituents are very small. This what does it mean lah. Main factor that dominating reactivity of nucleophile and electrophile, so steric effect, okay, that's what we discussed just now, and also electronic effect stem from electronegativity. This just basically if you have, for example, like this polarity there, so this become partial positive and this partial negative, so much easier for the nucleophile to attack this C lah, because it's already like less in electron, okay, in terms of density of electron. Okay, so the electronic effect can be inductive, polarization of bond, and also conjugation, distribution of pi bond. So that's basically if you have something like this, so that's basically conjugated nature lah. You can have a single bond. It's not, we don't say this is double bond, single bond, double bond, single bond, double bond, single bond. We are, if you see something like this, we call it conjugated nature lah, conjugated nature. Or more precisely, you can say is electron is delocalized. Okay, so basically when you have this thing, this is more stable, the stable structure. When you have the conjugation, when you have something like the alternating between double bond, bear in mind that when you see something like this thing, they have what we call it's not really, we cannot really say this is double bond, and then single bond. If you see this pattern, what actually you see is this is delocalization of electron. It's more like you can draw this thing and then it become like this. Okay, it's more like this thing is it's not double bond, but also it's not the single bond, it's in between. But because we cannot draw that in between in 2 dimension, that's why we draw this resonance structure. So this conjugation only occur when you find something, you have something like this, double bond, single bond, double bond, single bond, double bond, single bond. I mean, it's alternate. Okay, but this is not conjugation. If you see something like this and then something like this is not conjugation. This is just actual double bond. But if you see something like this, and then you have this, and then you have in between that there are no double bond, and then it's repeat again and again. So this is what we call conjugation. So what we call the reactivity of nucleophile and electrophile also being affected by this conjugation. Okay, next, steric hind. Let me see. Okay, so this thing. So let me remove the ink. Okay, so steric hindrance and more alkyl substituents make carbonyl compound less reactive toward any nucleophile. Okay, remember nucleophile is attacker. Okay, electron withdrawing group make them more reactive. Okay, so if you look here, this is what we call, look at this reaction. Let me take another color. Look at this reaction. So you have the carbonyl in water, and then you want to react this thing, and this is the what we call the equilibrium constant. So if you see that if you have acetone, the equilibrium constant is 0.01. What does it mean by that? Is that it's it's very small. I mean that it can go there, but it's not really favored lah to make a product. But then when you have acetaldehyde here, you have this H which is smaller than this. Remember, this is CH3. This also CH3, so it's bulkier. So that's why this only have one CH3, but then the one side is hydrogen, which is very small. So this cause the equilibrium constant tip to the product. So they are 1.06. So meaning that this is favorable because K is basically normally product over reactant. So if let's say you have above 1, then the product is favored lah in this case. So if you have formaldehyde, now both of this is hydrogen, which much smaller than CH3 here, then it will tip the product formation much higher lah. So that's why you can see 2000 times more reactive, this is more reactive towards the attack by the nucleophile. And also if you see this inductive effect, you have chlorine, and you know chlorine will pull the electron, so they have partial negative and partial negative on the chlorine side, and this will become partially positive. Okay, so this also favor the nucleophilic attack, so the nucleophile can sort of go inside there, so it's much easier. So that's why you can see is, even though it's bulky, you see the Cl is bigger, is big stuff compared to the hydrogen, but because the Cl also cause this inductive polarization of the bond, it also give way for the nucleophile to attack. And if you look here, hexafluoroacetone, you have the fluorine, and fluorine is big compared to the hydrogen. But then, even though it's big, it will also at the same time cause the polarization of the bond to the fluorine, causing the what we call, let me take the different color there, causing the carbon here is very partially positive there. So causing the nucleophile can attack easily here. If you look here, you see the electron constant tip to the very high 1.2 times 10 to the power of 6. So meaning that this hexafluoroacetone probably the most hydrated version of this lah. Let's see now how the carbonyl group is attacked by alcohol. What is the formula for alcohol? Alcohol is ROH, and you see the R, this R can be either H or can be either alkyl group, meaning that R equal to CH, whatever thing. Normally when we talk about R here, we are normally talking about this. Because why? Because if R is H, then you get water. We have discussed water before, and also water is not really, I mean, it's not alcohol. Water is water, alcohol is alcohol, so it's not normally associated with each other lah. But of course the water have hydroxy group, same like alcohol. So that's why normally when we talk about alcohol, the R here or any R is typically representing the alkyl group. So let's say alcohol can be, let's say R here can be CH3OH. So this is what? This is methanol, and then you have CH3, CH2, and OH. This is ethanol, and so on. Okay, so if you look this alcohol compared with the water, the one that we see just in previous slide, you have this what we call lone pair. The alcohol also has the same thing, CH3, and then you have OH, and this OH also, if I take this lah, the OH also have the lone pair there. So we can see that the behavior of attack by alcohol to the carbonyl group will be similar to this, what we call, to this more or less the water that we learned previously. That's why in organic chemistry, if you know how the arrow move from nucleophile to electrophile, then it's not really much mechanism that you need to what we call to hafal. It's more about understanding the mechanism. So that's why the mechanism of addition of alcohol follow the footstep of hydrate formation that we learned before. Just use ROH instead of HOH. So let's I remove the ink first. So it's more or less the same. The difference here is just, if you look here, this thing, they have the ET. ET is ethanol. ET here mean what? ET is CH3 is ethyl lah. CH3, CH2. So that is ET, ethanol lah, ethanol. And then because you have OH there, so you have the ethanol lah. Okay, so that's what does it mean by ET here. So ET here, so previously when we do with the water, you don't have this ET, you have only H. So that's why you get the OH here straight away. But now, because you don't have OH, you will end up with this thing, OR. OET lah, OR lah, OR. Because R can be representing the ethanol chain lah. So you get this, okay? And then if you look at this, let me take the different color. If you look at this oxyanion on the other side, so this oxyanion will also take from the behave like the nucleophile and take the what we call the hydrogen from the another ethanol, because remember here we only have ethanol, the pure ethanol, we don't have any water. So the only electrophile that this thing can attack is another ethanol. So if you look here, this ethanol and this ethanol, okay, these two ethanol here, this one behave like the nucleophile, this one behave like the electrophile. So same like water, water can behave like electrophile, water can behave like the nucleophile. So the product of reaction is hemiacetal. So this is hemiacetal. So you can see, you get the, when you do the reaction, you get something like this, okay. So you get hemiacetal, okay. Compare with the hydrate. Hydrate, here you have H, but hemiacetal you have this R here, okay. So let me remove this thing. Okay, so if you look here, the hydrate, the different, this is hydrate, the one that we learned before, hydrate, and the hemiacetal is this. You have this part, the R. The R here in this reaction is ethanol. So the ethyl group. So you have hemiacetal here. Okay. Hemiacetal is basically halfway to the acetal. If you look here, hemiacetal, you have still OH, and then acetal, you do some reaction more, then you get the R. Okay, mechanism. Let's talk about mechanism. Similar to hydrate formation. So we have learned before, but instead of water, the nucleophile is alcohol. And then let's focus on this thing. How they get the what we call the proton. Previously in water is easy because this thing just take from the water. But now here, this thing, what we call the oxyanion here, will take the proton either from the either from the another ethanol, so another alcohol. It can also take this thing from the same alcohol that is used, the very same nucleophile, from this nucleophile. This thing, the alcohol, they give they attack the what I call they attack the electrophile on the other side, and this what we call this charge, negative charge oxyanion will take the another hydrogen from the very nucleophile that is used. So that's what does it mean, the very same nucleophile. Or it can also take from the intermediate. So this is intermediate, this thing is intermediate, the one that is produced in between. So this oxyanion can take the hydrogen from this also. Okay, so there are three ways: from the another ethanol, from the very nucleophile that attack the intermediate, and the third is from the intermediate itself. So when actually which hydrogen that this oxyanion take, so is we don't know. I mean, no need to concern about that. The proton can always get where it's need to be for the next step of mechanism. So it doesn't matter where this oxyanion take the proton. What's more important is basically this addition part. Okay, this part, they will know where to take. They will take anywhere the available hydrogen. Okay, the available proton lah. Okay, so no need to concern about this. So you can draw this. You can draw here. This also, number 2 also correct. Number 3 also correct. It doesn't mean number 1 only correct. Okay. So ethanol in this case can act as a base and acid. So we established that before. So this is the different how the ethanol acting as a base. You have a nucleophile here attack the hydrogen. They also act as an acid, because why? Because acid, what does it mean by acid? Acid is something that is donate the proton. So meaning that it can donate the proton. So here the ethanol can donate his hydrogen. So this oxyanion will attack the hydrogen, and that's why this ethanol behave like an acid. Strong acid and base. Okay, strong acid and base. Let's say you have HCl and NaOH. Let me remove all the ink first. Okay, let me think. So make it easier. Okay, strong acid and base. HCl and NaOH. What does it mean by strong acid? Strong acid. Strong here meaning that is fully deassociate. Fully deassociate. For example, you have acid here. You put in water. This become H plus and Cl minus. Okay, so that's what does it mean by strong. Okay, if you have weak acid, it mean that it partially will dissociate. Some will dissociate, some will be stay as it is. Okay, strong acid and base increase the rate of hemiacetal formation because they allow proton transfer step to occur before the addition of carbonyl group. What does it mean? Let's see in this reaction below here. Okay, you have the what we call the aldehyde here, same like this at the top here. So same like here, aldehyde. But now the difference is that they use ethanol, same as ethanol, but now the different, they use acid catalyst, meaning that they put it in acid solution lah, acid solution, ethanol, and then they add acid together. What will happen is that the acid, because the acid give hydrogen, so this thing will start to get what we call protonation first lah. So this thing, this what we call the lone pair on the carbonyl group will attack this first, because this is small, so it's easy to be attacked by the aldehyde itself. So when that happen, so now it's already have this thing, and then it become what we call this positively charged, and then you have ethanol attack the what we call attack the aldehyde, and then you get more or less the same, you get the same thing, but the different now, what is the different now is that this happen very fast. The formation of the product, the hemiacetal, must be very fast. Because why? Because the aldehyde is first what we call first the aldehyde is first protonated on this thing lah, on the before the reaction with ethanol is protonated first before it react with the ethanol. Okay, so and then you can see this reaction. Please make sense of this. So it's the same idea with this, but just to show that when you make the reaction in the acid, the proton transfer step will occur first before the addition of carbonyl group, making the entire process much faster. Let's now talk about the formation of hemiacetal, particularly the sugar. So the sugar is type of hemiacetal that is cyclic. Okay, cyclic, hemiacetal. If you remember before, when we talk about the hemiacetal is like this. You have the OR, and then the OH, and then this R. We always denote this thing, the what we call the double arrow, like this, this thing, the equilibrium arrow lah, the equilibrium arrow, meaning that this hemiacetal formation is reversible. But then if let's say this thing can be converted into ring, for example like this, then it become more stable. Okay, hemiacetal formation is reversible, but it can be stabilized by being cyclic. Okay, so how it becomes cyclic? So let me remove first all the ink. So if you look here, hydroxyaldehyde, you have hydroxyl group, and then you have the aldehyde group here. Okay, so this hydroxyaldehyde, and then this thing, this alcohol, we learned before, alcohol can be nucleophile. Nucleophile can attack on this electrophile of this carbonyl group, and the same thing, but it's happened on the same molecule. Okay, so it will what will happen is an intramolecular attack. Intra here means that happen within the molecule. Okay, so it will attack this what we call the partially positive the carbon atom in the here, and then it will cause the pi bond of this double bond to goes to the oxygen become negatively charged, and then this oxygen negatively charged will find another proton. We have learned before, it doesn't matter where this negatively charged oxygen anion find its proton, but it's always find its proton. So in this case, we show that it's find its proton from its own intermediate, and then this thing oxygen become like this. So you get this cyclic hemiacetal. Okay, so the cyclic hemiacetal is still hemiacetal, but it's in ring form, and this is more stable. Okay, stability of hemiacetal gain when the carbonyl group and attacking hydroxyl group are part of the same molecule. This is intramolecular group. So if you look at the arrow there, here, you can see this is longer than the bottom one, meaning that the formation of cyclic hemiacetal is more favored. Okay, if you do the reaction, maybe 90% of time you will get the cyclic hemiacetal. It's very difficult for the cyclic hemiacetal to go back to this hydroxyaldehyde. So that's what does it mean by this arrow. Okay, this is intramolecular, within the same molecular reaction. Though cyclic hemiacetal is more stable, it's still in equilibrium with some open chain hydroxyaldehyde form. What does it mean? Let's say you put these two, you do the reaction, and then you do the reaction in a beaker. So you have cyclic, you have cyclic, 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 but the some part, there will be some open chain, open chain, open chain, okay? So that's what does it mean. But the number of cyclic is much more than the number of the open chain, okay? Because why? Because of the equilibrium is still more favorable to the production. It's stabilized in the cyclic hemiacetal. But remember, they are still the open chain because this it is still in equilibrium with the some open chain in hydroaldehyde form. Okay, for example, glucose in solution. We know glucose is like what? Glucose is like this. This is glucose. They have this OH, OH, and then this OH, and this OH, and then this OH. This is glucose molecule in the ring form. Okay, so in the ring form, when you have the sugar water, more than 99%, if you can have a very powerful microscope or whatever, you can find that 99% of the inside the solution is a ring form, but less than 1% you can still find the open chain form. Okay, OH, the Fischer projection lah, the what we call the OH and CS, whatever the thing lah. But like this lah, the open chain, they still available inside the solution, but the amount is very low, negative 0.01 like that maybe, but the amount of the what we call the ring is far more. So like this open chain glucose, open chain meaning that this lah open chain, this is open chain, this is closed chain or ring formation. Okay, so open chain glucose is less than 1%. Okay, so okay, let me remove this thing. So this is what I taught just now. So this is how they get the glucose. This open chain, this is what you call open chain. This is ring form or cyclic form. So you can see when this react, it can be either in ring form, cyclic form, or open chain form. But the cyclic form is more stabilized. That's why you have 99% of this form will be there if you do the reaction, and very less than 1% will you see the open chain. Okay, so this is basically what we call the open chain glucose. Okay, so you can see the glucose here. So you have 1, 2, 3, 4, 5, 6 carbon. Okay, 6 carbon. So this is linear form. We also call it linear form. Okay, so this is glucose, and the top one is what? This is aldehyde. The bottom one is alcohol. This alcohol. This is aldehyde. And same like this lah, hydroxyaldehyde, it can do the reaction by itself lah. Okay, and then this is a linear form or open chain. You can get this what we call, let me remove the erase a little bit here. Okay, this erase a little bit there. So this is the cyclic version. Okay, so beta D glucose. What is beta? Beta is this. Okay, if this thing, this is what we call Haworth projection. Normally we learn before the Fischer projection, the Haworth projection, and now we learn about Haworth projection. Last time we also learn what type of projection. There are many projection lah. The reason why they have many type of projection is just to show, it's just because of the limitation of the 2D drawing, because in reality all this thing is in 3 dimension. But because we cannot really, it's hard to draw 3 dimension in 2D paper, so that's why they come up with all type of projection lah. So this is Haworth projection. Haworth projection, they say that if let's say this OH at the top, then it's a beta. If this OH at the bottom, they call it alpha. Okay, so that is when the OH at the bottom lah, at the bottom. Okay, which OH? Because you see there are many OH there. There are many OH. So this carbon here, we call it anomeric carbon. Anomeric carbon, a carbon that is attached to 2 oxygen. Okay, so you have see the oxygen and the oxygen. So this anomeric carbon. So the what we call the designation of beta or alpha depend on the alcohol, the hydroxy group at the anomeric carbon. So you don't look at here, 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 but you look at this, the what we call the anomeric carbon here. The anomeric carbon, the hydroxy group, whether it's top or bottom. If it's at the top, then it's a beta. is at the bottom is a alpha. Okay, so let me remove the ink. So if you look here, this open chain can convert into this cyclic chain. You have the alpha and also a beta. As I said before, the alpha is when the hydroxy group at the anomeric carbon at the bottom, and beta is when the hydroxy group at the anomeric carbon in or the top position. So that is alpha and beta. Okay, in terms of mechanism, okay, so this thing, I mean, you have learned about the mechanism before, and this should be easy for you now lah. So you have open chain, so there is Fischer projection. So normally for glucose, we focus on glucose. For glucose here, we have 1, 2, 3, 4, 5, 6 carbon. One. Let me put in the color lah. You have carbon number 1, carbon number 2 here, carbon number 3, 4, 5, and 6. Okay, there are 6 carbon. Okay, so this glucose will turn into the 6-member ring. 1, 2, 3, 4, 5, 6 member ring lah. 6-member ring. So the what we call the reaction happen between this and also this. Okay, the reaction happen between this what we call aldehyde and the hydroxy group here. Okay, so they make a cyclic here. They will create the ring here. So when you do in the Haworth projection, so you draw this thing in Haworth projection like a boat, but it's not really a boat, but you draw like this. You put the CH number 1 here, the aldehyde group, number 2, 3, 4, 5, and so on. So you want to do a reaction, but we see that now here this thing and this is near, but we said before for the what we call for this reaction to happen, because why they attack here, not attack here? The reason because in order to get this ring, in order to get this 6-membered ring, you need to attack this what we call this hydroxyl need to attack the hydroxy at carbon number 5 is the one that need to attack the aldehyde. Okay, because why 6? This is relate to the conformation. Previously we learned why in the conformation class we learned why the 6-member ring, and also 5-member ring is the most common ring that you will see in organic compound, because they are less torsional strain, less whatever the thing lah. You need to refer back in the previous class lah about that conformation. There are reason why there are many molecules they have the 6-member and also 5-member. Rarely you will find something that is 3-member ring or more than 6, more than 7 like that. It's either 6, 5. Some, maybe you can have few others like 4-member ring, that might be, but it's not as much as the 6-member ring and 5-member ring. That's the reason why you need this hydroxy group is the one you will attack this the aldehyde group. So when you want to attack that, you see now for this to be attacked by this hydroxy group, it need to be near. But now the what we call the position now is not so right. So you need to rotate. Okay, so rotation here, this you need to look back at our stereochemistry and also conformation, because remember the single bond can be rotate. Remember the sigma bond can be free to rotate. When you have double bond, that cannot rotate lah, because this is sigma bond, you can rotate. So when you rotate, you need to know lah how to rotate counterclockwise and so on. So now you just put the what we call the hydroxy group near the aldehyde group. So now it can attack. Okay, now you can do your own. If let's say we ask about mechanism, you should know how to do the attack. You need to show how the what we call this, the lone pair from the OH attack which part on the CH2 and so on. And at the end of the day, you should get this. You should get either one here. Okay, you should get either OH at the top or either OH at the bottom. It doesn't really matter lah which one, but it doesn't really matter how you do the mechanism, because mechanism just show you the way electron move, but the conformation at the end, it doesn't really matter. You can draw the mechanism, and then at the end you just show there are two things. One, the OH at the bottom, one, the OH at the top. So when the OH at the top, this is beta. When the OH at the bottom, this is what I call this is alpha. Okay, in terms of the name here, if you look here, the name they are pyranose. What is pyranose? We know about the alpha and beta now, but what is pyranose? Pyranose is this: when you have the in organic chemistry in terms of sugar, the pyranose is they give the generic name for 6-member ring. Furanose, when you have 5-member ring, we call it furanose. Furanose. Okay, so because glucose will convert into 6-member ring. When I say 6-member ring, what does it mean that? 6-member ring, look here. So 6-member ring means that you have 1, 2, 3, 4, 5, 6. So this is what we call 6-member ring or pyranose form. Pyranose form. So that's why beta glucopyranose. Oh, no need to talk about the data. The D is just something related to rotation. So we don't concern about that for now lah. So beta glucopyranose, this is alpha glucopyranose. Okay, the difference is just the position of the hydroxy group. Okay, now let's talk about the leaving group. Okay, up until now, what we have seen is how nucleophile attack the carbonyl group, and that reaction is called nucleophile addition. For example, look at this reaction. This is basically the hemiacetal formation in base. In the previous slide, we use acid, but now let's say we use base. Okay, base catalyst mean that this formation of hemiacetal will be faster than normal lah, and faster than if they use only ethanol. Okay, so we compare this with the previous slide where we use acid. It's the same thing. It make the product faster, but in this case we use the base. Anyway, that's what we want to talk now. What we want to talk now about this product and this intermediate. Sometimes this intermediate is not stable. Normally intermediate is unstable. Some intermediate is more unstable than the other, causing the product here also not stable. Sometimes the product here, this thing, the OH, let me put in the different color. This thing is OR, right? OR. Sometimes this thing can leave the group, can leave the product or intermediate, okay, causing the making this the another reaction to occur. When this thing go out, then it's eliminated lah. So that's the not only the addition, because this is addition, but then when there are some living group in the reaction, and that living group is a good living group, then that living group have the probability to go out. When the living group go out, then the reaction is not only addition anymore. It can be undergo the elimination, or it can undergo also substitution. Okay, so this, look here. The product of nucleic addition to carbonyl group is not always a stable compound. We discussed that before, because they might be a living group in the product. Okay, so when the living group leave, then the reaction is not addition alone anymore, because another reaction can occur, such as elimination and substitution. So look at this, what I call at this thing. Okay, let me remove the ink first. So look here, this is addition. We learned this before, addition. Okay, this is intermediate. Okay, so in this intermediate, you see there are OR. Okay, OR is a good living group. Okay, good living group. So what can happen is that an ion, this what we call the oxy anion on the O here, can go here. Can this OR can leave? When this can leave, remember when you break the bond, another bond will be formed. So that's why this thing goes in. Okay, so you get back here. You get this thing. You get what we call the ketone here. You get this ketone. Okay. Okay, so this RO is a living group. So what will happen here? This thing is what we call elimination. So now living group are anions such as Cl, the chloride. Let me remove this first. Erase. Okay, living group is an ion such as this, the Cl. So Cl or OR, so OR, whatever the thing, and the RCO2. So it basically it's like this, COOR like this lah, RCO2. Okay, let me remove this. So that is a good living group. Okay, living group are anions such as that. So this, when you have this group in the intermediate, then it can be expelled by the molecule taking the negative charge with them. Okay, so for example, elimination reaction of carbonyl, that what you see just now lah, this elimination lah, meaning that this thing in the intermediate is unstable, it can get out by itself and causing this oxy and ion not to be promoted but rather to be eliminated, the making a new bond. So you get this back at the original, I mean that you get original back lah. Okay, so this is where there is a chance that it will lose again and that the carbonyl group will reform as starting material. So this is what we see here lah. Okay, this is elimination, the reverse of nucleophilic addition. It's just, you see here, it's just a reverse. So this is addition, this is elimination. It's just a reverse. You get back what you start with. Okay, so that's elimination. Another example is substitution reaction of carbonyl. For example, look here. If starting carbonyl group, okay, this thing, the starting material already have leaving group. Okay, if starting carbonyl compound contain a potential leaving group, so here this starting material already have this leaving group, the potential leaving group, then this leaving group have the possibility to leave the product during the reaction. For example, let's say you use this Grignard reagent. We have learned before, Grignard reagent, what will happen, they will behave like the nucleophile. It will attack this electrophile, this what we call this ketone here. They will attack this thing, and then same as normal, when you attack making bond, then another bond will be broken, and then you get this unstable intermediate. Okay, in this unstable intermediate, because you already have the OR, which is the good leaving group, this will detach by itself. Okay, and causing this, what we call this oxy and ion go make a bond by itself. So you got this, and this OR will just go just leave the group. RO is a leaving group. So what you get is this. Okay, if you compare this and compare to the original, you see a different thing, right? You see a different thing. Originally you have this, what we call OR, but here you have this ketone. Okay, this is ester. Okay, this is ester. This is not ketone. This is ester. Okay, this is ester. So you have ester, and now you get what we call the ketone here. Okay. In this Grignard attack to ester, we have not got back to starting material. Instead, we have made a new compound, ketone. Okay, so basically what happened now, this thing substitute with the methyl. Okay, so this is what we call substitution lah. Substitution. Okay, and then when you try to sort of like what we call go again, you do this again and again, you get another thing. Okay. Okay, so that is about leaving group. So another thing about leaving group, now it's easy to understand why the carboxylic acid derivative, this is carboxylic acid, so the derivative, okay, the derivative become target for this substitution or elimination reaction. Because why? Because if you look here, the derivative of the carboxylic is this. The derivative is that you change the OH here with the other thing lah. So because Cl is basically good leaving group, the Cl can become the anion. So it potentially behave like a good leaving group, similar to this OR and this O2R and so on lah. So now if let's say you use this as a starting material for your reaction, then it's easy for this Cl, OR, O2R here to become a leaving group. Okay. The OH here, if you might ask, why the OH now, the OH here doesn't behave like the leaving group? Why the OH can stay? Because remember, it's easy to understand why the carboxylic acid derivative, not the carboxylic, but carboxylic derivative. So if you have OH here is difficult to leave the group. Okay, OH is a bad leaving group. Bad leaving group meaning that it cannot leave lah. It cannot leave because they are strong base. They are unable to stabilize negative charge. What does it mean? Strong base like hydroxide, OH is a bad leaving group. Because why? Because OH is small. OH here, OH is very small. So meaning that the charge density the charge density is very polarized. We have learned before between the small and the big compound. So the small compound, if let's say they are polarization, then the charge is highly localized. For example, OH, the charge is highly localized at O. But then if you have a big nucleophile, this big nucleophile, even though they are polarization, but then the charge is more or less spread up compared to this small, relative to this small compound lah. So its charge density is localized, making it very polarized. When it's become very polarized, once they bind with something, it's hard for them to leave again. So that's why when the OH is bind to here, it's very hard for this become the leaving group. It not really will leave this thing voluntarily. Okay. Weak base like alcohol, halide is a good leaving group. Okay. Weak base like alcohol. Remember, alcohol is not this. This is, yes, it's hydroxide. This is hydroxide. Alcohol is you have OH, RO, you have R there. So it's bigger than OH alone. Okay. OH compared to the alcohol, OH is smaller. This hydroxide is smaller. That's why it's a bad leaving group. But this alcohol is big, then is constitute better leaving group lah. So weak base like alcohol and halide is a good leaving group. So for halide, so let me remove the color first. So for halide there, smaller one is bad leaving group because charge density is localized like we mentioned before. So halide is the halogen lah. Facebook, FC, L, BR and I. So you know this is smaller, this is bigger. This small, this big. Okay. Smaller, that's bigger. So this one, we call it bad leaving group lah. Bad leaving group. Leaving group. But the I here is good leaving group because it just can detach itself lah. Because the charge is not localized, so it's much easier for them to detach from other compound. So best leaving group in halide is I, Br, Cl, F, meaning that the iodide is better leaving group than Br. Br is better leaving group than Cl and fluoride lah. Fluoride ion is bad leaving group because it is smaller. For example, ester preparation from acyl chloride. So let me remove this thing. So let's see the ester preparation from the acyl chloride. So you see this is addition we learned before. So now you have base taking the what I call the proton, and then you get like this. What I want to show here is this intermediate. So you see here this anion, the oxy anion, it will not take the ash. Okay, because why? Because first they don't supply the hydrogen here, the hydrogen or water, whatever, maybe they put in not in the water or not in alcohol. But then here in this intermediate you have this good leaving group, the Cl. When the good leaving group leave, then the bond is broke, so meaning that another bond must be formed lah. So that's why it become like this. Okay, so Cl an ion is a leaving group. So ester preparation from acyl chloride. Okay, so that is how the leaving group cause this is elimination because the Cl just being eliminated from the group. So you have addition here, addition reaction, and you have elimination here. So ester preparation from the acyl chloride. So the base here, if you look here, the base is needed, commonly used is pyridine because it's remove the proton for alcohol once it attack the carbonyl group, because they want to remove this lah, so that the reaction can go forward. So now what we have seen now is we focus on carbonyl compound. Okay, we have what until now we learn about carbonyl compound from the beginning of the slide until now. You have learned about carbonyl compound. So we first went in detail about nucleophilic addition to familiarize you with arrow pushing, and then we briefly introduced the concept of leaving group and talk about the substitution and elimination. So using the knowledge, you can let's try to understand briefly the saponification. Okay, saponification is basically hydrolysis of ester. We see what is ester. Ester is you have CO, you have O, and then you have R, lah. So this is ester. Okay, hydrolysis of ester using base. Okay, look here, you have ester, you use catalyzed base. So what will happen during that thing is addition elimination. Okay, the mechanism is addition and elimination. So the name for this, making this what we call uh, hydrolysis of ester using base, is called saponification, or making the soap lah, making the soap. Okay, so now let's see this thing. Okay, so I already put the link, so you can just click that and what we call and see lah. So let's see, let me put here first. Okay, so let's see just roughly about this thing. You can watch the entire thing, but the one that I want to focus, let me remove the sound first. Okay, the one that I want to focus is the mechanism. Okay, so in the soap you have this. Okay, lithium, they use lithium hydroxide, not yet, they have this okay, so this, so in the soap they have something like this, they call it this is what we call the fatty acid with the glycerol triolate. This is basically in the oil lah, olive oil. So and then what they do is that this is ester. If you look here, you have O, you have R, and then you have O, you have R. So this is ester. Okay, so we learned before that when you put ester, when you try to hydrolyze ester in NaOH, what does it mean is that you put this what we call the oil in the NaOH, and then what will happen, this thing will happen. So the mechanism for this is the what I interested lah, this the thing that I'm interested with. So if you go let's go to the mechanism itself. Okay, so this is the mechanism. Okay, maybe it's small for you to see it, but you can just go to the link and see the big what I call big screen. So what I'm interested is how this thing, how the what I call the lone pair attack this thing and get all this thing, and this will be broken and so on. So try to make sense of the reaction, because you can understand this based on what the knowledge you have before, the addition, the addition and the elimination, the substitution, what we have learned before. You can use that to understand this thing. So you can just watch until the end, it doesn't really matter, but then what I'm focused here is the mechanism. So the experiment itself to show you how this mechanism happen in the real life lah. So you can watch this how many minutes, 20 minutes, is up to you. So you can watch, but I'm focused on the this thing, the saponification itself. Saponification is basically making a soap lah. Okay, because sapo is mean soap. Okay, saponi is soap, making soap. Okay, so you can watch this, and let's go back to the let me remove this. So let's go back to here. Okay, so what else? Okay, so what we have learned, you can apply to a simple alkane. Let me remove first the, what is the my heading? Wait, yeah. Okay, so what have we learned before, you can apply it to simple alkane and others lah. For example, electrophilic addition of alkane. You can see this thing. Okay, we have learned before about carbonyl, but now we go for the alkene. Okay, electrophilic addition of alkene. So you see here, you have this is what, this is nucleophile, because you have hydrogen bromide, you have is what we call you have this electronegative atom connected to the hydrogen. So this will behave like the electrophile, because it's much easier for it to, because the hydrogen can be deficient in electron. So what will happen, this is a double bond, so double bond is rich in electron, so it can act as a electrophile, not electrophile, nucleophile. Okay, so the nucleophile will attack this thing, nucleophile attack on HBr on alkene. So what will happen is that nucleophilic attack of when you attack here, what will happen, you have this hydrogen there, but then the Br will be detached. So this Br, the same Br will attack this carbocation on this intermediate lah, because when you try to attack, the double bond will break, make a bond with the hydrogen here, with hydrogen, and then you will left with the carbocation. We have learned carbocation before. So carbocation is can be behave like a electrophile. So the bromide and ion that is left before, it can come back and attack on this carbocation. So you get this thing. So this is just nucleophilic. This is what we call electrophilic addition. Electrophilic addition. It's addition. It's you add thing. You add thing to the double bond. So that's addition. So this for example for symmetrical alkane. Okay, and then so this is the what we call the step. I mean the mechanism, the outline of the mechanism. I already explained before, but you can read all these things. But then, what if you try to attack using the hydrogen bromide also attack the unsymmetrical alkene? Okay, for example, this. Remember, phenyl here mean this thing, the benzene ring lah, more like benzene ring. So now you have something like this, and then you know this is you have the ash, and then you have ash here. So that's what does it mean by this picture. So now you add with the HBr. Okay, so now HBr here, the first thing what will happen is that the attack by the nucleophile to the electrophile. So this is nucleophile, this is electrophile, this electrophile, this is the nucleophile. Okay, so the nucleophile will attack this, so they will attack that. Okay, when this attack, what they take the hydrogen. Okay, and then Br same like above here, the Br will go somewhere in the solution, but then they will Br also can come and attack the electrophile. The Br here, an ion here is nucleophile, will attack back the carbocation. So now you have Br and then you have ash plus and Br minus. So where to put this, because this is unsymmetrical, where to put this? Okay, where to put this thing? So there are two possible outcome, but which one is preferred? Okay, so let me remove this thing, erase ink on all sides. Okay, so you have two possible outcome, either the Br attack here or the Br attack here, the Br attack here. So meaning that there are two type of carbocation ion that is possible. Because when you try to, when here, if you look here, when the double bond attack the hydrogen, take the hydrogen, it will create the carbocation ion. So when you have something like this, pH here, the carbocation ion can be either this pH and then plus here, and also it can be also here, plus here, pH. Okay, okay. Where is the ash? Okay, in this case we don't draw the ash, but remember this thing meaning that they have another ash here lah, mean that they have ash here, the ash here, and here you have ash here, and then also ash here lah. That's what does it mean lah. So now the question, where is, so this another ash lah to make it full. Let me put full. Okay, so basically depending on where the ash goes, okay, the ash goes, let me put ash, why the thing like this? Okay, depending on where the hydrogen goes, it will either go here, either go this way. Let me put this thing, either go here, or go here. Okay, so depending when the hydrogen goes, it will create different type of carbocation ion. So this carbocation ion is what? This is primary carbocation ion. So this one is primary carbocation ion, this thing, because they are only attached to one carbon only here. Okay, so this is primary carbocation ion. So this is secondary carbon, this is primary carbocation ion, this is secondary carbocation ion. Because why? Because the carbon here, this thing, carbocation ion here, attached to two. So this phenyl is also carbon, so this also carbon here, so they are secondary. So the more the higher the secondary, for example the tertiary carbocation ion is more stable than secondary, is more stable than primary in terms of carbocation ion lah. So this is more stable than this lah, more stable. This less stable lah, less stable. So normally when you make a product, you want a stable product. So the reaction favor the stable, the reaction will go and favor the stable carbocation ion lah. In this case, this lah. So this is more stable. So because of that, this is stable carbocation ion. So the bromide, the bromine that is going out just now will come back and attack the carbocation ion here lah. Carbocation ion. That's why you get this thing. You get the Br here instead of getting Br here. Okay. So that's you get this thing. So if you understand the mechanism, you can predict even if you don't know about Markovnikov rule. What is Markovnikov rule? The Markovnikov rule is this lah, the one that you just see just now. That is the understanding behind the Markovnikov rule. But the Markovnikov rule is basically, you can read this. I mean, let me remove all the color first. You can read this thing. But the Markovnikov rule state the hydrogen end up attached to the carbon of the double bond that had more hydrogen to start with. Because for example, you have this thing, you have phenyl here, and then you have hydrogen. Let's say I draw the hydrogen. You have 2 hydrogen here and 1 hydrogen here. So Markovnikov rule said that if you have HBr, okay, HBr, the hydrogen here will attach to the carbon of double bond that have more hydrogen to it. So meaning this, they will go here. They will go here instead of here. Instead of here, they will go here. So because this part, this carbon here have more hydrogen. Okay, so that is a Markovnikov rule. But the understanding behind the Markovnikov rule is about this, is related to the carbocation and how the stability of carbocation. So that's why if you understand the mechanism, you can predict even if you don't know anything about Markovnikov rule, but at least you should know lah. Also lah, Markovnikov rule is just like a shortcut. The hydrogen end up attached to the carbon of the double bond that have more hydrogen to start with. So if you look here, the knowledge, if you look everything now, the knowledge that you learn from the Carbonyl Group, addition, arrow pushing, is very useful later on. For example, it will become very easier now if you understand the mechanism, how the arrow push, what happened when the arrow move here, and then nucleophilic, and then electrophilic. So you not end up menghafal. Kalau tak, you akan hafal, you akan penat lah. Tapi kalau you macam faham, dia jadi macam, benda tu macam tak banyak pun reaction. Dia macam how the arrow move here and there, and break bond, attack bond, carbocation, and so on. So it's not really difficult if you understand the thing. Okay, let's talk about the substitution and elimination. Normally, you heard the word SN1 and SN2, E1 and E2. SN here stand for substitution, whereas the E here mean elimination. The number there mean the number of reaction. If you have SN2, mean that 2 reaction occur simultaneously, giving you the bimolecular transition state exists. But then, if you have 1 here, mean that the substitution reaction occur after the another lah, meaning that step by step. So unimolecular transition state exists, meaning that you have 2 transition state, 1 and then 2, meaning that it doesn't occur simultaneously. It's separate transition. You will find the 2 separate transition state. So that is SN1 lah. It's happen 1 by 1. Okay, for this I will not go in detail, but you should study this video. So this video give you the idea how to choose between SN1, SN2, E1, E2 mechanism. So if let's say you understand what have been taught so far, then you will have no problem to follow along this video. So I will left this to you to watch this video. This is only 18 minutes, so hopefully you will understand the difference between SN1, SN2, E1 and E2 mechanism. And going for the last slide, this is how the organic chemistry relate to ourselves. Okay, we have our body, and inside our body there are many chemicals. So where is organic chemistry play their role? Okay, so looks at the carbohydrate. So this is one of the compound that relate to organic chem. So carbohydrate can be simple and also complex sugar. Simple sugar like monosaccharide, disaccharide, oligosaccharide, and complex sugar can be like starch, fiber, glycogen, cellulose. Okay, for example, the one that we see just now when we talk about the hemiacetal, the cyclic hemiacetal, we talk about the monosaccharide, the glucose part. Okay. So this we have learned before, how the glucose turn into the cyclic. From the open chain, they turn into the cyclic, the 6-membered ring, cyclic. Okay, so basically this is the glucose that we see just now. Previously we learned how this glucose can if it is alone, if it's alone like this, then we call it like glucose and so on lah. But then this glucose can also make a bond to another glucose, and this, when you have a lot of glucose connected with each other, you are getting the polymer. Okay, polymer. Okay, so this become complex sugar. Glucose itself, the one that we learned before, glucose itself is a simple sugar. It's easily metabolized in our body. But when this glucose connected with another glucose and connected with another glucose, then you have something complex. We call it, in terms of glucose, if the monomer is glucose, then we call this thing as a cellulose. Okay, so that is a complex sugar. Okay, you can have starch, fiber, glycogen, cellulose, and so on, whatever the thing lah. So this is cellulose. Cellulose, where you get the cellulose? From the cell wall of the plant lah. So you take the leaf and then you see the cell. So the cell wall here, inside the cell wall, this cell wall, not the cell. Inside the cell you have the nucleus, mitochondria, whatever it's saying lah. But the cell wall that make up the plant cell, if you go there, you will find the cellulose fiber. So inside the cellulose fiber is all this thing. So this is the complex carbohydrate. And one thing that we need to understand a little bit is glycosylation. Glycosylation is a process where carbohydrate, so this carbohydrate is basically whether it's a simple sugar or complex sugar, covalently linked to other macromolecule. So if you have this carbohydrate, typically the one that's undergo the glycosylation is not so complex sugar lah, not so complex carbohydrate. Some complex carbohydrate can also make the glycosylation, but typically in human body you will find that oligosaccharide, meaning that the carbohydrate that have a few connection will make a bond with something, for example maybe the protein. So this is protein. So this is oligosaccharide, is a we can call it simple sugar, still simple sugar. So the connection between this is called the connection between this oligosaccharide and also protein. This thing we call it glycosylation. Okay, so glycosylation is a process where carbohydrate covalently linked to other macromolecule, lipid and protein. Okay, so next we talk about lipid. Okay, so let me remove all the ink. Lipid is a fat. So we seen this fats when we talk about the saponification previously. Okay, how the mechanism of saponification, making the what we call soap using the fat or oils. Okay, so example of lipid is this lah, fats, oil, wax, and also lipid can also like be a phospholipid, glycolipid. So if you look at the cell, so if you look here, this is this is plant cell. If you look at human cell they don't have cell wall. So this is human cell, this is nucleus, and they are mitochondria and so on. So the cell here, you have the what you call the outside the cell, we call it outer layer. Not outer layer, meaning that the outside the cell lah. So between this, they are like the barrier there. For example, let me put here. So between this, inside this cell what we call cell, we call it cell skin lah, or membrane. So this cell membrane is made of from this lipid bilayer. So you can see here. So you have something like this. So this is the amphiphilic molecule or triglyceride or whatever. This is lipids. Okay, and then you have another one like this, another one. Okay, so we know that this what we call the amphiphilic molecule. For example, the lipid lah. Lipid is amphiphilic molecule. Why? Because they have the hydrophobic and hydrophilic part. So the tail here, the what we call the tail here, the tail here is hydrophobic, and the head here is hydrophilic. Okay, so if you look at this image at the bottom here, you can see now the hydrophobic part. Let me put another color. So this hydrophobic part here, they will sort of like be together. Okay, and then the outer part is hydrophilic. So that's why the lipid bilayer here, this we call lipid bilayer, they turn out like this, because normally hydrophobic, they will tend to gather with another hydrophobic. Okay, hydrophilic will tend together with hydrophilic. So hydrophilic here make contact with the outer world. So like darah ke, air ke, our blood, the water. So that's why here the outer environment here is hydrophilic. So that's why the head is facing the water lah. So this is example of compound lipids. The phospholipid here is a compound lipid. Okay, this is phospholipid. This is phospholipid. Okay, and then the derived fatty acid, glycerol, cholesterol, steroids, and so on. And then about nucleic acid. So let me remove all the ink. So nucleic acid is this. Okay, so you know in the cell, so this cell membrane, the blue one, cell membrane, the one that we just see just now, the lipid bolide, this thing is basically this thing. And then inside the cell they have many stuff, and then inside the stuff there are nucleus. Inside the nucleus you have chromosome, and inside the chromosome you have what we call the DNA. Okay, so DNA here, the most important thing, if you look at the DNA here, you can see how the DNA is made up. Okay, if you look here, you have this is what we call deoxy sugar. That's why or very specifically deoxyribose, because ribose have the five membering. So you have 1, 2, 3, 4, 5. Okay, so that's why the name is deoxyribose. What does it mean by deoxy? If you look at the what we call the H2COS, let's say this is our glucose just now. Before we learn about glucose, you see the glucose have OH, and then H. When we talk about deoxy, what does it mean? Deoxy mean that one here they are H, mean that they are because OH mean hydroxy group. So when you remove one hydroxy group and you put it the H, then this is what we call deoxy sugar lah. Deoxy sugar. So okay, so in case of the what we call the DNA, they use a ribose. Okay, ribose is 5 membering sugar. So that's why you see there are 5 membering. It's not like glucose. So deoxy sugar, this part. Okay, so this you have a deoxyribose connected to the phosphate. So this is phosphate. Let's say I put here. So this is phosphate. Okay, so you can see the backbone for the DNA is deoxyribose connected to phosphate, and then you have deoxyribose, and then there's phosphate. Okay, so this is backbone for DNA. So that's why they said phosphate deoxyribose backbone. Okay, and then here, if you look here, this is what we call the nucleotide. This thing is a nucleotide. We call it nucleotide. Okay, there are 4 nucleotides, which is adenine, or we call it A, and thymine, T, and then we have what we call guanine, G, and also the cytosine, which is C. Okay, you don't need to know very detail about the structure, but at least you should know this thing. A, what's the name? Adenine, thymine, A, then T. The structure you don't need to concern lah. And G and C. So in DNA, A always what we call A always with T, G always with C. Okay, so this is the GC. Okay, this is AT. Okay, so when you do DNA sequencing, normally you heard you maybe have seen something like GATTCAT, whatever. When people show something about DNA sequencing, you see the numbers here. You see the letters like AT, CG, whatever. So this is basically this thing lah: adenine, thymine, guanine, cytosine. Okay, when the DNA is double helix. When the DNA is manifest, the A is always connected with T, G always connected to C. Okay, so in between this thing, between the phosphate deoxyribose backbone is the nucleotide, and nucleotide will pair with each other. Adenine will pair with thymine, guanine will pair with cytosine. Okay, so you should know that thing lah. So let me remove the ink because it's too much now. Okay, so what is the purpose of DNA? The first is store genetic code, that you should know lah, because it's like a blueprint of our life, blueprint of our thing. And then DNA also what they do is that they do transcription. For example, DNA to mRNA transcription, and then translation mRNA to amino acid. So for example, in order to get a protein, let's say you have a protein, let's say hemoglobin. Hemoglobin is basically your red blood cell. Hemoglobin. Okay, hemoglobin is a protein. So in order for a body to make this, they need to get instruction. So where they get the instruction, they get from the DNA lah. So in order for DNA to instruct the body to create this hemoglobin, first DNA must do transcription. So when DNA do transcription, what will happen? They create mRNA. And then this mRNA will undergo translation. Translation and give you amino acid. And amino acid combined with each other, you get what is this? We'll get the protein, because protein is basically amino acid lah. Amino acid, you have a lot of amino acid, they combine together and then you get a protein. So that is what is protein lah. So in order for protein to be produced, you need to get instruction from DNA. So how they do it is basically by first transcription process, where the DNA convert into mRNA, and this mRNA is used to create to instruct the formation of an the coding for the amino acid production. Not production mean that this mRNA will tell how this AA should assemble, so that it can create the correct protein, which is hemoglobin in this case lah. And then DNA also can involve in replication. For example, DNA to DNA. For example, when the mother's pregnant, so part of the fathers will go to the child and a part of the mothers goes to the child. So that's basically copy of the genome, copy of the genetic material from the parents. So that is replication. They just make a copy. Okay, so you make a copy, undergo all this what I call the mitosis and so on. So this was basically replication. So that's what the what I call the biological function of DNA that is related to organic chemistry. Okay, and also you have ribonucleic acid and then amino acid. Let me remove this thing color first. Okay, and then amino acids, peptide and protein, also a compound that have this organic molecule within it. Okay, some protein do not fold correctly unless they are glycosylated. So we have learned this here. Okay, glycosylation. What is glycosylation? So some protein do not fold correctly, because for protein to give, for example, for protein to do their job, correctly, they need to be fold correctly lah. So some protein do not fold correctly unless they are glycosylated. So that's why the importance of glycosylation. Some protein not stable unless they contain oligosaccharide. Okay. So for example, integral membrane protein. So for example, if you look here at the bottom here, you see the membrane, cell membrane. So if you look here, this is integral protein. You see this thing. So this is integral protein. You can see you have the protein there, and then you have oligosaccharide there. Okay, so this connected with the glycosylation lah. Okay, so the purpose for this is to receive and pick up signal for immunity purpose. And then in order to sort of like to what we call to connect correctly, you need to understand the importance of stereochemistry. For example, let's say you create a drug for COVID-19. Okay, you need to make sure that the drug that you create can really detect what you want to detect lah. For example, when we create a vaccine, COVID-19 vaccine, what we use is that we put the spike protein. The spike protein is this lah. The coronavirus, you have spike protein there. Okay, spike protein there. So you need, in order to create a right drug, you need to make sure for vaccine, basically they just take this and then they put in your body. You put in your body there. This is you put in your body. Let me put another color lah. Put in your body. So in your body now you have the when you take vaccine, basically you take the weakened virus lah basically. So they take this spike protein, put in your body. So this this spike protein will sort of like trigger the immune system, and then the triggering happen by this lah, by the integral protein. They will sense lah, what is this, what is that. So they trigger the immune system and they tell the body, okay, now we find the virus, so please generate the antibody, and then the antibody come, and then they will kill whatever virus that come to you later on lah. So the vaccine is like that. So the important thing is that you need to make sure the glycolization is important here, is because they allow you to, what we call, the proper glycosylation is important, because if you do glycosylation incorrectly, then they will not detect lah, they cannot detect, trigger the reaction. Okay, so this is important when you try to create a drug. You need to make sure the stereochemistry for the drug is correct lah. For example, we have learned before thalidomide and so on. Thalidomide, we have like L-thalidomide and whatever, S-thalidomide and so on. So we know that the difference between these two isomer is just the flip-flop. I mean the stereoisomer, they are stereoisomer, but it looks similar but it's not similar, and we see that the difference of the outcome that they can produce. So it's important, same like glycosylation lah. Glycosylation also, when you try to mix protein and carbohydrate in order to create a new drug, you need to make sure whether it affect their stereochemistry or not. Is it the correct stereochemistry that you need or not for the drug design? Okay, so that's the importance of stereochemistry previously lah. In terms of creating the drug and how it's linked with the glycolization. So I think that's it for what we call for this video. So hopefully you can answer your question well in the final exam. Good luck and thank you.